Hello viewers, welcome to video number 106 of the channel MALACHEMPHILIC, and video number 106 is the 46th episode of Chemical Thermodynamics, and the topic of this episode is Gibbs free energy, a thermodynamic parameter, why needed? Let's see. Before going to Gibbs free energy, let's discuss what is spontaneous process. Already I told you earlier, spontaneous process means which occurs without any external aid. That is spontaneous process. And then coming to the prediction of spontaneity. How can we predict that this process will be spontaneous or this reaction will be spontaneous? Already while teaching entropy, I explained that total entropy change, that is entropy change of the universe, which is equal to entropy change of the system plus entropy change of the surroundings. If this total entropy change of any process or reaction, if it is positive, that means greater than 0. That means if it increases greater than 0, then that process or reaction will be spontaneous. On the other hand, if delta S universe is less than 0, that means if the total entropy change of the system and surrounding decreases during a process, then it is non-spontaneous. And if delta S universe is equal to 0, that indicates that equilibrium is reached. This we have already studied from the part of entropy. But that means from the total entropy change, that is the entropy change of the system and surrounding together, we can predict the spontaneity of the process or reaction. But the problem is, it is very difficult to calculate the entropy change of the surroundings. Say surrounding is releasing heat to the system. Then surrounding is a very bigger part. So from which part heat is released, or if the system releasing heat to the surroundings, then which part of the surrounding is absorbing. So it is complicated, very difficult to calculate. So what we need? We need a system-based parameter to predict the spontaneity. That means the parameter which depends only on the system, not on the surrounding, so that it can be easily calculated. That kind of thermodynamic parameter is needed to predict the spontaneity. Okay, now let's discuss the system-based parameter. Already we know that energy. Okay, see, every system wants to gain the stability. How? By decreasing its energy. So, if in a reaction or in a process, if the energy is released, that means system will try to go towards that direction. That means that process will be spontaneous. Okay. On the other hand, if in a process or reaction energy is absorbed, in that case energy of the system will increase. Energy increase means stability will decrease, and that is not favorable position. So then that process will be non-spontaneous. So we can understand that if energy increases during a process or reaction, then that will not be spontaneous. On the other hand, if energy decreases, then that will be spontaneous in terms of energy, right? Now, so what is the conclusion? Conclusion is all exothermic reactions are spontaneous. Exothermic means energy is released from the system, so they are spontaneous. Energy released means energy decreases, so spontaneous. And all processes where energy is released are spontaneous. Okay? But the question is it universal truth? Is it universal truth? Let's see. Okay. Now, say liquid. Liquid is converted to vapor. Okay. Now here, while converting to vapor, that is vaporizations or boiling, here it is absorbing heat. Absorbing heat means energy increases. Energy increases means it should not be spontaneous, but we know that this vaporization is a spontaneous process. Okay, it should not be spontaneous because here energy is absorbed or heat is absorbed. Energy is absorbed or endothermic. Okay, still it is spontaneous, but it is spontaneous. We all of us know that vaporization is a spontaneous process, right? Okay, next example you take, this is example number 1. Dissolution of sugar in water. Dissolution of sugar in water. And this is endothermic. Energy is absorbed. Endothermic means, according to our concept, it should not be spontaneous because it is, in this case, energy is increasing. It is endothermic but spontaneous. Many such examples are there. Say, ionization of ammonium nitrate in water. Ammonium nitrate, this is solid, plus water. So, ammonium ion, ionization plus nitrate ion. This is delta H positive. Okay, energy increases. Still it is spontaneous. Okay, delta is positive but spontaneous. Then another example you take. This is your, say, hydrogen plus iodine. Okay, that is 2 hydrogen iodide. Here also delta H positive, but it is spontaneous. Okay, take another example, that is decomposition of nitroglycerin. This process is, or this reaction is exothermic. Exothermic, but it is non-spontaneous. Means you have to, it explodes when physical shock is applied. That is non-spontaneous process. External aid is required. So, here energy decreases but non-spontaneous. All this energy increases but spontaneous. Energy increases means it should be non-spontaneous, but they are spontaneous. Here energy decreases means it should be spontaneous, but here it is non-spontaneous. So, only with the help of energy of the system, always we cannot predict, or always we cannot make the correct prediction about spontaneity. Okay. Then we take in terms of entropy. If we take the entropy of the system, only system, okay, because already I told our need is one system based thermodynamic parameter. We know entropy of the universe, that is system plus surrounding, it can give the correct prediction, but difficulties are there, right? So entropy of the system, let's see what is the problem. See this one, water, that is liquid water at -1 degree centigrade, okay, it will become ice, right? And -1 degree centigrade, it is a spontaneous process. Spontaneously water is converted to ice, right? But liquid is converted to solid. That means the entropy decreases till the process is spontaneous. Okay. Here what is happening? Energy is released. Entropy change of the system will be is equal to minus, energy is released, minus Q by T. That means it is less than 0. Entropy of the system decreases till it is spontaneous. Okay. Now take another example, that is dissolution of hydrogen chloride gas in, this is number 1, this is number 2. Hydrogen chloride gas in water to form hydrochloric acid. Hydrochloric acid. Okay. This is exothermic reaction, exothermic process, and it is spontaneous. So it is spontaneous. Okay. But entropy is decreasing. Okay. Gas is just dissolved in water. Randomness decreases. Here what is happening? Randomness decreases. So entropy decreases. So here entropy decreases but still spontaneous. Here also entropy of the system decreases, still spontaneous. So only with the help of entropy change of the system, it is not always possible to predict the spontaneity. Okay. Now you see, if we consider one or two earlier examples, say once again we are taking some examples, some more examples, okay. Some more in the sense, same examples, we'll try to explain once again. See, this one, liquid is converted to vapor. Okay, here what is happening? Energy increases because it has to absorb energy. So therefore non-spontaneous in terms of energy. But entropy increases, liquid is converted to vapor means randomness increases. But randomness increases So entropy increases, that is greater than 0. Okay, that means spontaneous in terms of entropy. Spontaneous in terms of entropy. Okay, acha. Same this example once again we'll see. Dissolution of hydrogen chloride in water, already I told you this is exothermic process. So this process, once again I'll write. Dissolution of hydrogen chloride. So dissolution of HCl gas in water. Already I told you process is exothermic. Okay, energy decreases, right? So therefore spontaneous in terms of energy, but already I told you randomness decreases. Non-spontaneous, delta S decreases. So non-spontaneous in terms of entropy. Okay, so now exactly what we need. Okay, so what we need, okay, we need one system based, already I told you, system based thermodynamic parameter where both this energy term and this entropy term, means entropy change and energy change, both are present, and there will be compromise between this energy and entropy. So what we need? We need the system based thermodynamic parameter. Exactly what we need? We need system based thermodynamic parameter where energy and entropy both are present and a compromise between energy and entropy occurs, right? And these thermodynamic parameters are, one is A, which is equal to E, internal energy, minus T S. S is entropy. This is known as Helmholtz free energy. And another one is G, which is equal to H minus Ts. H is the enthalpy of the system. This is your Gibbs free energy. Right? Now you see, if I consider the first example, this example where liquid is converted to vapor, energy, in terms of energy, it is non-spontaneous, but in terms of entropy, entropy increases, so it is spontaneous. Okay. But this overall process is spontaneous. That means here in this particular case, this entropy overcomes the energy, so the reaction becomes spontaneous. And in the second case, where dissolution of hydrogen chloride gas in water to form hydrochloric acid, entropy decreases. In terms of entropy, non-spontaneous, but in terms of energy, it is exothermic, it is spontaneous. In this case, this energy term overcomes the entropy, so overall the process is spontaneous. Okay. So in these two functions, you see both energy and entropy terms, these are present. Okay. And here it is at constant volume related to internal energy. No, here it is at constant pressure. Gibbs free energy G is equal to, we know, H minus Ts. Okay. G is equal to H minus Ts. Now delta G, that will be is equal to G2 minus G1, right? So delta G will be is equal to G2 means H2 minus Ts2 minus H1 minus Ts1. So delta G is equal to H2 minus Ts2 minus H1 plus Ts1. Okay. So delta G is equal to H2 minus H1 then minus T. So S2 minus S1. So therefore delta H minus T delta S. So delta G is equal to delta H minus T delta S. Right? So both this function, that is both this thermodynamic parameter A and G, where both energy terms and entropy terms are involved, that can be used for the prediction of the spontaneity. But in A is equal to E minus Ts, this is at constant volume. So it is at constant volume. Okay, here we maintain the volume constant. But G is equal to H minus Ts, here pressure constant. Okay, temperature isothermal automatically constant. So generally the process or reaction we carry out at constant atmospheric pressure. So this G, that is Gibbs free energy, is more important in predicting the spontaneity of the process or reaction, right? So now let's see. So therefore Gibbs free energy change during a process is more important. Now we'll see what is Gibbs free energy. G is equal to, look at here, H minus Ts. Okay, H is the total energy present in the system and this S is the unavailable energy or the energy which cannot be used for doing the useful work. That is unavailable energy to do useful work, or it is non-useful energy. That means in case of that heat engine, the energy which goes to the sink. Okay. And therefore, this is total minus unavailable energy. Okay. Or non-useful energy. So, this minus this will be the useful energy. That indicates the amount of energy which can be converted to useful work, or energy of the system available to do the useful work. So total energy minus unavailable energy, that is the G. Okay, Gibbs free energy. That means it indicates the useful energy to do the work or amount of energy which can be converted to work. Right? So this is the significance. Okay. Now see in this expression, this enthalpy is total heat content, is a state function, temperature state function, entropy state function. So Gibbs free energy is a state function. And this Gibbs free energy is extensive properties, okay, which depends on the quantity of the substance, amount of the matter present in the substance, right? Now we'll see one thing. See, we know that delta S universe, from this we can predict the spontaneity, which is equal to delta S system plus delta S surroundings. Okay. Now, delta S surroundings, what we can write? Delta S surroundings, that will be equal to, here, say, system is absorbing heat, surrounding is releasing heat. That means minus Q of your system divided by temperature at which the heat is released. Achha, minus Q system, what we can write? Minus delta H system enthalpy. Okay, enthalpy change, heat absorbed or heat released is equal to that change in the enthalpy. So minus H system divided by T, right? So look at here, delta S universe is equal to delta S system in place of surrounding minus delta H system by T, we can write it. So from here what we can write? We can write T delta S universe is equal to T delta S system minus delta H system, right? That means, see, so interesting, T delta S universe is equal to minus delta H system, right? And then minus I have taken common, so delta H system minus T delta S system. So T delta S universe is equal to minus, what is this? Delta H minus T delta S, nothing but the delta G system, change in the Gibbs free energy of the system. Look at here. So change in the Gibbs free energy of the system is equal to this change in the entropy of the universe multiplied by T. See, entropy of the universe, if it is positive, then multiplied by T will be positive. Okay. So it is negative, means it will be negative. So this one, and we know that delta S, from delta S universe we can predict the spontaneity. Okay, and T delta S universe is equal to delta G of the system. That means from delta G system also we can predict the spontaneity. Only thing is that sign is opposite. So therefore when delta S universe greater than 0 or delta, it is negative, related to negative sign, delta G system less than 0, okay, Delta G universe greater than 0 means delta G universe is less than 0. Then it is spontaneous. Okay. Similarly, delta S universe less than 0 decreases, and delta G system, now it has come to system, greater than 0, then it is non-spontaneous. And if both are 0, then that is in equilibrium. Okay. So delta S universe is 0. That means delta G system also will be equal to 0. That indicates the equilibrium state. Right? So now we got this function or this thermodynamic parameter which depends only on the system and by which we can predict the spontaneity, because it is the combination of both energy and entropy term. So compromise is possible. They are compromising, so finally it is giving the correct prediction of the spontaneity of the process. Hope you have enjoyed. Thank you.